Good morning. Okay, in the last lecture, we had a look at some photographs of different types of foundations, and we realised they are shallow foundations which are constructed near the ground surface. Normally they're constructed using things like the backhoe on what you might call a JCB. And then there are deep foundations where we either bore a hole to depth of, say, 10, 15 metres, or we either drive a column 10 or 15 metres into the ground, called pile driving, or we bore a hole to the same depth and fill it with reinforced concrete to create a deep foundation. And most foundations fall into one of those two categories. And what I said we'd do this time is, we will look at the bearing capacity of the first type of those foundations, the shallow foundation. Before I move on from this slide, the pictures I use are often from things around campus, and this particular photograph is, well, there's a strip footing running along here, and it's actually been combined, not just a strip footing to support some columns, you can see columns going on in various cases, but along this bit, a retaining wall, and this is all part of the newer of the Earth Sciences building, built about 2 years ago. And so, if you keep your eyes open as you walk around town, as you walk around campus, and have a look over the fence, never enter a construction site, but look over the fence and have a look at what's going on, you can often see a lot, and it can improve your comprehension of what's going on in construction by observation. Okay, so we covered that last time. This is just a summary. We said for shallow foundations, we've got pads, which are square footings founded 1 metre, maybe 2 metres below ground level. Similar aspect ratio in the two directions, often used to support individual columns. We've got strip foundations, which are long in one dimension, used to support load-bearing walls, and rafts to support the whole structure. And what we're going to look at is a mode of analysis that covers all that category. So, we're going to start with a I always hate it when people say very simple, because it's not. We're going to start with the most straightforward case we can, which is going to be a strip footing on a clay soil. So, a strip footing is where we've got something where we can think of it as being long in one dimension relative to the others. So in analysis, what we do is we go to the middle of that part, that footing, and we consider a section of it of unit length and because we've got footing alongside it which is identical to what's in our unit length on both sides, the deformation occurs only along that axis. So we can treat it as a two-dimensional problem. Provided your strip footing is fairly long in comparison with its width in that direction, then for most of the footing it would deform, unaware of what's going on at the ends. So we're going to have a footing, and the dimension we're going to look at here is our dimension we're going to call B. So that's the first point we're going to look at. And I say we're going to look at undrained clay. Why are we looking at undrained clay? Well, to keep life nice and straightforward, we've got a material here where the shear stress at failure equals CU. So, for this particular case, when we have a failure surface, we're going to get shear stresses develop on the failure surface. And in a general case in soils, we have to say that the shear stress on the failure surface is C dash plus sigma dash tan phi. So when it's drained, we have to know what the effective stress is locally on the failure surface in order to work out what the shear stress is. But for this particular example, undrained clay, we can estimate it directly from the void ratio, or in a real site investigation, what you'll do is just measure the undrained strength and assume that the void ratio hasn't changed in the period between measurement and construction. Okay, we're actually going to consider a situation where the undrained strength, so we've got a site like so, and we put down a borehole, and we're going to take a number of samples from various depths, like so, and we're going to plot the Moore circles of failure. So when we plot out tau against sigma, we're going to get a whole series of, I've just drawn a half circles there, and we're going to estimate a single value of, I'll label it at this end because I've made my diagram a bit cluttered, Cu. In other words, we're assuming for this particular example that Cu doesn't vary with depth. This isn't a necessary assumption. We can perform the analysis when Cu varies with depth. But the mathematics just gets a little bit more complicated, so we're picking this example to illustrate how the bearing capacity analysis is undertaken. This example is a good approximation for a heavily over-consolidated soil horizon, where because you're on an unload-reload line, due to the stress history of the soil, the void ratio is fairly constant with depth. So this might be applicable to construction on over-consolidated clay like London clay, Oxford clay, Galt clay, which are present in many parts of the south of this country. So, our first assumption, the case considered, is cohesive soil, toilet failure equals Cu, and we're going to further assume that Cu doesn't vary with depth. We've got plane strain conditions. It's a shallow foundation, so we've already said that means the depth to foundation level is a lot smaller, no, not a lot. The depth to foundation level is smaller than the width of the foundations. We're going to make the assumptions that the footing is rigid, so we're going to say it deforms as a single block. So we're going to ignore bending deflections of the footing. And when you put something in the ground which is stiff, made of reinforced concrete, as a first approximation, that's usually a good assumption, because usually soil is far less stiff than reinforced concrete. We're going to assume the soil is perfectly plastic. What do I mean by that? Well, we're going to conduct stress strain tests on our soil, where we plot the shear stress, or normally we plot the triaxial deviator stress, but the two are related. So we're going to plot sigma 1 minus sigma 3, the diameter of the Moore circle, and we plot it against, usually, axial strain in our test. And real soil behaviour we saw last time looks something like so. And we're going to assume in our analysis that the soil is rigid plastic. So we're assuming there is no deformation. I should be better off using a coloured pen, I think. So there's no deformation before failure. And then after failure, it fails at constant shear stress. what that constant shear stress is, we've got a choice to make whether we use peak strength or constant volume strength. Now, if we assume that displacements around the failure surface are constant, don't vary much, so that everywhere is mobilising the same proportion of strength, it's safe to use the peak strength because all the soil will get to peak strength together. If, however, the soil is very compressible, so we push down on the foundation and we get a lot of movement locally, but further away we get no movement, we ought really to use that strength to avoid the problem of progressive failure. Okay, there's a couple other details I've included on there. This idea of the soil having a unique strength, we're going to perform an analysis for a particular strength, and if it softens with displacement, if it softens with time, the analysis is not applicable. And so implicitly, that leads to the assumption that we're doing an undrained analysis, we're assuming that the drained strength is higher than the undrained strength. In geotechnics, it's usually a safe assumption when you increase the stress on soil to assume that the drained strength is higher than the undrained strength. When you decrease the stress on the soil, it's the opposite way round. So when we load foundations, normally the undrained loading scenario is the more critical, because as we increase the stress, in time the soil will consolidate, get denser and get stronger. When we dig excavations, it's the other way round. We dig an excavation, we unload the soil horizontally, and there the undrained strength is greater than the drained strength. It makes excavations particularly hazardous. It's why nobody ever enters an undrained excavation. If you dig a trench to put, for example, sewer pipes in the ground, very often that trench will stand vertically open and look perfectly safe. But we never ever go into those trenches to work until we've got some sort of temporary shoring in place, because with time the soil's getting weaker, and if you left it long enough, those holes collapse. And so this uncertainty about what happens there with the softening leads to a safety-first approach, which is always use some sort of shoring protection. Don't always hold the size of a trench up, but you normally create a box within which people can work, so if the trench does collapse, it's still safe. Okay, and we're going to make the assumption, which is the soil above foundation level has no strength. We've said, and I'll draw this in a moment, the reason for this is just that it makes the analysis more straightforward, and we're ignoring a component of strength, and therefore it makes the analysis slightly safer than real life. And the last thing we're going to do is we're going to guess at a failure mechanism. So what we have in your notes, and I have it on the projector in a moment, but it's always nicer to start by actually drawing on a diagram, is this sort of scenario here.